Hello everyone. Today we'll discuss about diode approximations. So in diode approximations, we'll discuss about the first one is ideal diode approximation, or it is also called as first diode approximation. And the second one is second diode approximation or practical diode approximation. And the third one is linear piecewise approximation. So before to this, we already discussed about the VI characteristics of the diode. So the VI characteristics of diode is, when you draw it, it is like this, the forward biased, and when it is reverse biased, it looks like this. So this is the forward characteristics, and this is reverse characteristics. Okay, so this is the VI characteristics of a normal diode. Now, if we consider the ideal diode approximation, then ideal means we assume that the diode starts conducting as soon as you apply a external voltage. It means there is no depletion region inside it. Therefore, as soon as you apply the external voltage, it starts conducting, as well as there is no forward resistance. Okay. So in the normal diode, when we consider this VI characteristics, we can see that up to this particular level, this is called as the threshold level. It means because of the depletion region, there is no flow of current, or a very minimum flow of current is there. But after this threshold, or after the depletion region completely vanishes, then the current increases linearly. Okay. So here also we can observe that it is not increasing suddenly, but it is increasing linearly, and this linear increase in the current is due to the forward resistance. Okay. So, but in the ideal diode approximation, there is no forward resistance, there is no depletion region. So therefore, it conducts current as soon as you apply a small external voltage. This is the forward characteristics. When you consider the reverse characteristics, whatever reverse voltage you apply, there is no flow of current. Okay. So it behaves like open circuit. Now, when we also consider, or when we if we write the equivalent circuit of a diode in a circuit, for example, if this is a circuit, this is a circuit. In this circuit, if you want to replace this diode, then if you want to replace the diode with some equivalent circuit, a short circuit means a conducting wire. Simply, we'll connect a conducting wire which does not have any resistance, and therefore, as soon as you apply a small voltage, it starts conducting. Okay. So this is the ideal diode approximation. The second one is second diode approximation. In second diode approximation, the depletion region is considered. It means the diode starts conducting after certain voltage. For example, if we are considering a silicon material diode, means a diode made up of a silicon, then after 0.7 voltage, it starts conducting. And after 0.7 voltage, there is sudden increase in current. Okay. It means depletion region or barrier potential is considered, but there is no forward resistance. RF is not considered. Okay. So this is ideal approximation. Second diode approximation. And the third one is linear piecewise approximation. If I, okay, so before linear piecewise approximation, if you want to write the equivalent circuit of this second diode approximation, then it will be a voltage source. Means instead of a diode, we can use a voltage source with some depletion region. For example, if it is a silicon, then we'll use 0.7. Okay, so up to 0.7, there is no flow of current, but after 0.7, there is increase in current. Third one is the linear piecewise approximations. So in linear piecewise approximation, we have to consider the depletion region, that is barrier potential, as well as RF. And the equivalent circuit of this is a voltage source with the forward resistance. Means a diode can be replaced by a voltage source and a resistance in case of the linear piecewise approximation. Okay, so this is about the diode approximations. Now, the next concept is DC load line. If you consider the same forward characteristics, okay, and if you consider this is forward resistance RF, and the voltage across the diode is VD or VF. Okay. Now, when the current flowing through this is I, and from KVL, if we write the equation for the circuit, then it will be IF RF plus VD minus V. So V is the voltage source, equals to 0. And if I equate it for the voltage source, then it will be equal to IF RF plus VD. Now, this is the current axis and this is voltage axis. I'll obtain 2 points now, and I have to assume 2 things. The first thing is, if VD is equals to 0, then I get V is equals to IF into RF. And in the same equation, if I substitute IF equals to 0, then V is equals to VD. I'll get that. Sorry, so this is point B and this is point A. Okay, so initially when VD is equals to 0, you'll get V is equals to IF RF. So we'll get this point. And when IF is equals to 0, V is equals to VD. You'll get this point. Okay, so IF is equals to 0 means on this axis. And once you get these 2 points, and if you join these 2 points, then this line is itself called as DC load line. And wherever this DC load line intersects the VI curve, this point is called as quiescent point or Q point.